starts. So the first thing is remember that we won't have any class on Wednesday um, because we've got, what is it? Veterans Day. And then next week, Wednesday, I'll be attending a conference. So I will not have any class that day either. So to make it easier for you guys, I will delete the there we go. I will delete the Zoom for next week, Wednesday, so you guys won't be confused that you have to show up to class next week, Wednesday. All right. So, hold on a second, guys. Okay. So we are going to be starting a brand new unit today. We are going to be doing chapter 50, and I will actually want to go into chapter 51 for class. I'm so confused. Hold on a second. Yeah. Okay. So we're going to go through chapter 50, and actually we're going to start chapter 51 as well today. All right. So in terms of our chapter 50 class, right, we are going to do the musculoskeletal system. So we will have the bone, joints, cartilage, tendons, ligaments, and skeletal muscle that we're going to be discussing, right? And this will really set us up for chapter 51. So in terms of our musculoskeletal system, we'll start off with the bone and the joints and the cartilage, tendons and ligaments. So we're going to be looking at connective tissue, right? So remember, guys, connective tissue is basically a type of tissue that is regarding cells scattered amongst an extracellular matrix, and that extracellular matrix can be calcified like bone, gelatinous like cartilage, or it can be liquid, fluid like blood, right? But for us, we are going to be looking at cartilage and bone. And when we're thinking of bone, the very first thing I think is important for us to discuss is the fact that bone actually comes from cartilage. So, you know, when you look at a fetal skeleton, it's actually laid out with hyaline cartilage that eventually ossifies to become bone. All right. So in terms of the structure and function of bone, why do we have bone? Bone is obviously important to protect our internal organs. You know, the skull protects our brain, the ribs protects our lungs and our hearts. It's also important to provide bony attachments for muscles and ligaments. It's important to help with mobility because, you know, it acts as levers for us to have functional movement. And of course, it's important for storage, right? Storing marrow, storing different minerals like calcium and phosphorus. Another thing about bone that's very important is that it's highly vascular. You've got a very rich blood supply coming to bone, and it's metabolically active. It's completely alive from birth to death. Your bone is constantly remodeling, it's constantly reshaping throughout your entire life. So it's important for us to remember the cellular components of bone, right? So, you know, the first set of cells that we need to really think about are our fibroblasts. So fibroblasts are and fibrocytes are connective tissue cells that are important for collagen production, right? Osteoblasts lay down new bone, right? Remember when you think of blasts are like immature cells that are usually making our extracellular matrix, synthesizing the extracellular matrix, secreting the extracellular matrix. So your osteo for bone, blast for these types of cells, lay down new bone. Your osteocytes are your mature bones that live within the bone matrix, and then your osteoclasts are responsible for bone resorption. So in terms of or ground substance and collagen fibers, this is what, I have to turn off my email. This is what makes up the extracellular matrix. right? Um, your ground substance has your minerals like your magnesium, your phosphorus, your calcium. It has the extracellular fluid. It has the hyaluronic acid. And then your collagen fibers give your bone the tensile strength, and that makes up the majority of your extracellular matrix. So your collagen fibers are allowing for a bone to have weight upon it and being able to bend and withstand that weight without breaking. So your bone is made up of basic units known as osteons, right? And you have two types of bones. You have your trabecular bone, which is your spongy bone, which is not soft like a sponge, but is kind of shapes in that spongy way to allow for the bone to be light. So you tend to have it in areas where you need the bone to be light, like the skull, for example. And then you have compact bone, which is bone that's resistant to a lot of stress. You tend to find it in areas where a bone is very dense. So in terms of bone being able to manipulate and remodel over time, well, bone is really able to do this because it can alter its shape and density in response to mechanical stresses. And so take, for example, if someone wears braces, right, their jaw is realigned because of the pressure that the braces put upon the tooth, which is pegged into the jaw itself. Okay, so the idea is that the bone is going to remodel based on the direction of the stress. Now, in terms of whether or not you do have stress, if you don't have stress on the bone, therefore there isn't much remodeling and the bone eventually begins to atrophy away, right? It begins to demineralize over time. Now, remember, bone comes from cartilage. So endochondral ossification is a process of how cartilage is replaced by bone, right? So you have that hyaline cartilage in your early development in utero. And as bone becomes nutrient rich from its blood supply, chemical signals come in and ossifies the bone, right? Send signals for the chondrocytes to die and be replaced with osteoblasts, which will lay down new bone. And then the osteocytes will live within that bone. So as the bone ossifies over time, this happens throughout basically the majority of the growth of childhood, then you end up with what's called your epiphyseal plate in your long bone. So epiphyseal plate is your hyaline cartilage plate. That hyaline cartilage plate is constantly laying down new bone so the bone can grow. Okay, and once that epiphyseal plate is all done, signals are sent that the bone is no longer going to be growing anymore, and as a result, the epiphyseal plate will ossify and become the epiphyseal line, and the bone will no longer be able to grow in length. Now, articulating cartilage is always going to be there unless you have some type of disruption to it from maybe you having some type of osteoarthritis or some kind of destruction to the joint itself. But that articular cartilage is usually there. So like I mentioned before, bone remodels in response to stress, right? So bone is laid down wherever it's needed, and where it's not needed, it's resorbed, right? And in terms of the epiphyseal plate itself, if there's any damage to the epiphyseal plate and it's no longer able to lay down new bone, that bone will not be able to grow in length anymore. So it's very important that if there is any fracture in a bone, it's checked to see if the epiphyseal plate is disrupted in any way, because if it's disrupted, the bone will not be able to grow. Now, as we age, of course, the bone will decrease in mass, right? And bone density will decrease over time. And of course, certain disease processes like osteoporosis, for example, your bone density will decrease as well. So in terms of, speaking of fractures of bones, right? Bones go through the epiphyseal plate and the bone. So the epiphyseal plate is a growth plate for someone that is growing. Yes, Dan. So in terms of the healing of the bone, okay, let's say you have some type of fracture, because bone is has a very good rich blood supply, it will probably bleed, right? So a hematoma will form in the inflammatory phase. And then because cartilage is needed for bone, fiber cartilage is actually laid down. So remember we talked about the fact that hyaline cartilage is what makes up the fetal skeleton, and your new bone comes from the hyaline cartilage. Bone that is fractured comes from fiber cartilage. And as a result of that, the fiber cartilage is laid down and a bony callus is formed. That bony callus will eventually ossify, and over the few weeks to a year, it will remodel. So one of the reasons you want to make sure you set your bone when you break it is because once that bony callus is laid down and it begins to remodel, it's going to remodel in terms of the mechanical stress that's put upon it, right? So when the bone is set, like in a cast, okay, you don't have a loss of movement, you don't have a loss of stress upon it. So it's not going to be forced to remodel in a direction that it should not be remodeled in. It's going to be remodeled in the direction that it's set in. So this is why you set a bone whenever it breaks. Now, in terms of your different joints, right, your joints are your articulations. They're your contact point between the different bones, all right? Your joints are able to permit movement, allow you to have purposeful movements and coordinated movements. And in terms of the different type of joints, I mean, you've got joints that are ball and socket joints or hinge joints in the cranium. You've got joints that are slightly movable, like the pubic symphysis and the intervertebral joints. The joints themselves are going to be categorized by what makes up the articulation. So for example, if the articulation between the two bones is due to fibrous tissue, it's a fibrous joint. If the articulation between the two bones are due to cartilage, it's a cartilaginous joint. And then you have what's called diarthroses or synovial joints, which are made up of a synovial capsule. So your fibrous joints are your joints that are united with this fibrous tissue, like interosseous membranes between the tibia and the fibula. Remember, the fibula is not a weight-bearing bone. It's a bone that's usually used for muscle attachment, right? So as a result of that, it kind of is attached to the tibia, grounding it, and it's attached through these interosseous membranes. And then you have your cartilaginous joints, which are connected through either fiber cartilage or hyaline cartilage. So fibrous joints include joints like I mentioned before, those that are syndesmosis between, joined through that interosseous membranes like the tibia and the fibula. But sutures in the cranium are also an example of a fibrous joint. And the gomphosis between the teeth and the mandible are also an example of a fibrous joint. But your cartilaginous joints are joints that are either joined with fiber cartilage or hyaline cartilage. The fiber cartilage joints are symphysis, usually found along the midline. So your pubic symphysis, your intervertebral discs, those are all symphysis joints. And then synchondroses are usually two bones that are joined together that have like a really bony connection. And those are joined by hyaline cartilage. So those are considered to be a synchondrosis. Your diarthrosis allows for you to have lots of mobility. So you tend to find that in an area where you need lots of mobility, like the knees, for example. You have these capsules, and these capsules are joint capsules that are made up of a synovial capsule, which has a synovial membrane. And the synovial membrane secretes synovial fluid. And that synovial fluid allows you to lubricate the joint itself. When you have these diarthroses, they tend to stabilize the joint really well, especially because it's a joint that tends to have a lot of movement. So the capsule itself will be lined by the synovial membrane, which secretes the synovial fluid. And of course, it will have the hyaline cartilage as an articulating cartilage between the two bones. But the capsule in itself really allows for great movement. And there are lots of accessory structures within the actual joint capsule itself, which allow for you to have these many different movements, right? And still be able to stabilize the joint. So you can move around one axis or two axes or even three axes and still have a stable enough joint itself. In terms of cartilage, there are three types. We talked about hyaline cartilage already. Then there is fibrocartilage that we talked about. And the last type of cartilage is elastic cartilage. So hyaline cartilage is the most abundant, fibrocartilage is the strongest, and elastic cartilage is usually found in places where you need to kind of shape out the organ, like the nose or the air, the external air. You got to shape out that part of the body, but it doesn't need to be very strong. Now, cartilage in itself is, composed primarily of water, and its matrix has a lot of collagen. And that collagen and elastin, and even those proteoglycans that make up the cartilage itself, is really important to spread that load, right? That's applied to the actual joint. It helps to decrease stress and limit wear and tear, especially because there's like movement within the joint. So Shannon, it's fibrocartilage, elastic cartilage, hyaline cartilage. Okay. So it really allows for you to tolerate tension, okay, and resist that compression that happens between the joints themselves. One thing I would keep in mind is that you want to make sure you guys are not mixing up tendons and ligaments, right? Ligaments connect bone to bone. They help to stabilize the joints from bone to bone, okay? But tendons connect muscle to bone. So they are really assisting more in the movement. So when you think of a muscle, the muscle has connective tissue known as an epimysium that wraps around the actual whole muscle itself. And then that connective tissue kind of continues on and forms that tendon that will attach the muscle to the bone. So speaking of muscles, right? The muscle part of the musculoskeletal system is what's contracting to have the bone move, right? Because it's attached to the bone via the tendon. So muscles are about 40% of your total body weight, and they're very important in, yes, mobility, but also providing stability as well. A lot of times people don't realize that your muscles are contracting, at times to help give you tone, right? And to keep your posture. Okay. So the skeletal muscle itself is providing strength to the body, providing stability, and yes, allowing for movement as well, but really helping to like distribute the load amongst the body. So importantly, right, each muscle cell is considered to be a muscle fiber. Okay. And those muscle fibers are encased in a plasma membrane known as a sarcolemma. And then all those muscle cells or muscle fibers are grouped together in bundles. Okay. And those bundles are called fasciculi. So those fasciculi are bundled together to make the entire muscle. And connective tissue is going to wrap around each of these. So you have the endomysium, which is wrapped around the actual muscle fiber or muscle cell. You've got the perimysium, which is wrapped around the fasciculi or the bundles. And then the epimysium is wrapped around the entire muscle and continues on to be the tendon. Okay. So the muscle itself is striated, and it's striated due to what's known as sarcomeres. So the sarcomeres are those contractile units, and they're made up of actin and myosin and other regulatory proteins and structural proteins. So for example, you have troponin, which is an important protein complex, which manipulates another protein known as tropomyosin. Tropomyosin is important for blocking the myosin binding sites on the actin. Okay, so that's controlling the contraction. It's controlling whether myosin is binding to actin. So within the sarcomere, right, I'm sure you guys have seen these 17,000 times before, right? One sarcomere is from one Z disc to another. And the idea is that you want to pull the Z disc towards the midline, right, which shortens the sarcomere. With every shortening of the sarcomere, the actual muscle cell will contract, okay? So you have your thick filaments, which is your myosin, and your thin filaments, which is your actin. And the myosin heads grab onto the actin and pull them towards the midline, right? So the idea is you want to get rid of the H zone, pulling the Z discs together, shortening the sarcomere, essentially shortening the entire muscle. So all of this is done because of all these individual components. And these individual components are important, right? Because troponin is important to manipulate tropomyosin, and tropomyosin is important to manipulate the action of myosin. Okay, so essentially, this is all done through action potentials. And I know you guys know this, you've seen this many times before, right? The action potential travels down the axon when it gets to the end of the axon, right? Something like acetylcholine would be released, that neurotransmitter, to cross the cleft, changing that electrical signal into a chemical signal. Acetylcholine cross the cleft, bind to the plasma membrane on the muscle cell. Now that membrane invaginates into the cell in an area known as the T-tubule, so that when the action potential travels down the plasma membrane into this T-tubule, it causes calcium gates to fly open, and the calcium that's stored in this sarcoplasmic reticulum is released into the cytoplasm. And that's great because once calcium is released, it's going to bind to troponin, and troponin is going to move tropomyosin out of the way. That way, myosin can grab onto actin and pull actin towards the midline. And that whole process is called the sliding filament theory, right? You want to be able, through ATP, because the myosin head is an ATPase, through the energy of ATP, to be able to have myosin grab onto the actin. Once myosin grabs onto the actin, right, the phosphate is released. And that energy that was stored allows the myosin head to pull actin towards the midline. Then the ADP is released. The new ATP comes along. When the new ATP comes along, it allows for the myosin head to release from actin. So this stage right here is what happens when you're in rigor mortis. When you die and you're in rigor mortis, there's no more ATP because you're dead, right? So basically you're stuck right here without being able to release the myosin head because there's no ATP to release the myosin head because you're not making ATP anymore. You were making it up until the moment you died, but the moment you die, there's no more ATP. So you're stuck in this cross bridge, not being able to release the myosin head. So that's how rigor mortis comes about. So overall, you need to have this muscle contraction because you want to be able to pull the bone, produce the movement, right? So when we go to chapter 51 and we're looking at all of the different disorders, you know, the disorder can cause for disruptions in the first step, which would be here at the neuromuscular junction. If the neurons don't work, like in ALS, right? If the motor neuron is not firing because it's dead, then it can't send the message across to the muscle. Then the muscle can't contract and this portion can't happen. And then if the sliding filament theory isn't occurring, the muscle cannot contract. Therefore, the patient cannot move, okay? If we're looking at something like muscular dystrophy, in a muscular dystrophy, the patient has a, like a Duchenne's, they've got a mutation in dystrophin. Dystrophin is no longer able to stabilize the sarcomere. The sarcomere falls apart, the muscle cell atrophies away, you can't contract the muscle, there's a lack of mobility. So regardless of whatever, you know, is the disease that we're looking at, the bottom line is this whole process from the neuromuscular junction to the sliding filament theory has to occur. If there's any disruption in any of the regulatory proteins that make up the sarcomere, any disruptions in the action potential, and whether there's firing from the nerve to the muscle, then you're not going to have that mobility that you need. You're not going to have that contraction in order to pull on the bone and produce the movement. So essentially, you have to make sure that the sarcomere contracts. You have to get the two Z lines to move closer together. You have to get the myosin head to bind to the actin. You have to form the cross bridge. You have to have available ATP because you want to make sure that you have the energy for the process to occur. You have to have you have to have calcium. Without calcium, you're not going to be able to move tropomyosin out of the way because it can't bind to troponin to tell troponin to move tropomyosin out of the way. So calcium in itself is important. So if calcium is absent, there will be no muscle contraction. Calcium needs to be present to bind to troponin, move tropomyosin out of the way, and uncover the binding sites. If you're not using the muscle, you're going to lose the muscle, right? If you don't use the muscle, the muscle is basically saying, you know what? I'm not being used right now. I don't need all these proteins. All these proteins that are right here, I don't need them because I'm not being used. So the muscle gets rid of some of the sarcomeres, and therefore it has less proteins. Therefore, it's now a smaller cell. A smaller cell leads to a smaller tissue. A smaller tissue leads to a smaller organ. Therefore, the muscle begins to atrophy away. Does that make sense, guys? Perfect. Any questions on this? Okay, so essentially what I'm going to do now is I am going to have us move into chapter 51.